Thanks to tiny differences in the swirls and whorls of humans' fingerprints, it's possible to identify the specific person a set of fingerprints belongs to. And we can do something similar with the various species of plants and animals out there, even though most of them don't actually have fingers. Hi, I'm Kate, and this is Minute Earth. The kind of fingerprints I'm talking about start not with fingers, but with light. When light hits, say, a pine tree, certain wavelengths of light reflect off the tree. Some of these reflected wavelengths are ones we humans can see, but others are in the invisible part of the spectrum. If you could get a snapshot of all the light, both visible and invisible, that a pine tree reflects, you'd come up with this, what scientists call the species' spectral fingerprint. Let's compare that to the snapshot for a different tree species nearby, say a magnolia. At first glance, the spectral fingerprints of the two species look similar, just like the actual fingerprints of two people. But, like the tiny differences in those fingerprints' swirls and whorls, there are tiny differences in how the two tree species reflect light, thanks to their slightly different chemical composition, crown and microscopic structure, water content, and more. Since all tree species vary slightly in these kinds of characteristics, each species of tree has a distinctive spectral fingerprint, which means it's possible, based on a tree's spectral fingerprint alone, to determine its species. And that has tremendous implications for our planet. Tree ecologists can run fancy images from planes and satellites through computer programs trained on the spectral signatures of thousands of different tree species. And the programs can identify the species that live there. The programs can even find trees that aren't doing well and figure out the particular reason they aren't doing well. Like an oak tree is supposed to have a fingerprint like this. If it has a fingerprint like this, it's drier than it should be, suggesting drought. If it has a fingerprint like this, it's having trouble photosynthesizing. It probably has a disease. You may have noticed that we've only been talking trees so far. See, scientists have been working with trees' spectral fingerprints for a particularly long time. So they've been able to amass a big library of different tree species fingerprints and start putting them to use. But as far as we know, every species, from corals to fish to polar bears, reflects light in a slightly different way, and therefore has a distinctive spectral fingerprint. So scientists are exploring other branches of the tree of life. They're working to document the unique fingerprints of more and more species, and figure out what we can accomplish with those fingerprints. Things like finding polar bears on vast stretches of ice, and assessing the health of huge underwater reefs, which are, of course, tasks that are already possible without spectral fingerprints. But they generally require a lot of slow, difficult, in-person research, often in places where it's very hard to work. Spectral fingerprints are helping scientists collect data about specific individuals and species more quickly and easily than ever before, as are other remote approaches like trail cams, GPS collars, environmental DNA, and acoustic monitoring. With these kinds of strategies, maybe we'll be able to save certain plants and animals before all we have left of them is their fingerprints. One group working hard to use spectral fingerprints to study and conserve biodiversity is the ASCEND project, a National Science Foundation-funded biological integration institute led by Janine Cavender-Bears, Phil Townsend, and Peter Reich. The ASCEND team is using spectroscopy in all sorts of ways, from finding and mapping sick trees to prevent the spread of disease, to tracking biodiversity over time to see if efforts and policies are making a difference. In addition to advancing knowledge, ASCEND is training the next generation of integrative biologists to understand how life's variation is connected across scales and impacted by global change.